Hello and welcome along to a video taking you through your case study of the impacts of climate change on the tundra biome in Alaska. This is the schema that we're going to have to help us to navigate our way through it. This will appear quite a few times in the course of our presentation just to let you see the big picture of where it all fits together. Take a few moments here now. You can see in red that there are three main subsections that we're going to address. First of all, the temperatures are rising faster in Alaska than in most other parts of the world. I'm going to give you some evidence for that. We're going to look at patterns over time and patterns over space, and then we'll take a look at the potential, it is likely to happen in the future. Spoilers, it's going to continue to rise. So our evaluation here as a result of that, because the temperatures are rising faster, is going to lead to a cascade of catastrophic consequences. We're going to take a look at two of those. The second box in red here is the tundra is now seeing significant wildfires in a way not experienced in the past 11,000 years. We're going to take a look at the increased lightning, the wider geographical area that it covers, and what are known as zombie fires. We'll take a look at one particularly graphic example of that, and a Tuvok fire in 2007, and then looking ahead into the potential. What's the impact going to be as this trend continues? And the second in the cascade of catastrophic consequences is the permafrost thawing at an alarming rate. Can you see the value judgment words coming in there? Setting up some positive feedback loops. We're going to look at two things. One is called a thermokarst lake, which is basically a melt lake, and thaw slumps, which is whenever the soil slumps down, falls down because of the thawing of the thermofrost inside it. And then the potential impacts, we're going to see some more of these positive feedback loops. I'll explain those on the way through. So three main headings. Temperatures are rising faster in Alaska than most other parts of the world. As a result, there's a cascade of catastrophic consequences. The tundra is seeing significant wildfires in a way not experienced in the last 11,000 years. And the permafrost is thawing at an alarming rate, setting up concerning positive feedback loops in motion. Keep that clear in your head when you're learning this. Learn through that. That'll help it all stick together for you. Okay, let's just remind ourselves of where we are in the world when it comes to this. The tundra area here is represented in this area in the blue line. This black line is the Arctic Circle. And you can see this as you look down from the North Pole. There's North America, there's Alaska, there's Russia, there's the British Isles just up there. This is the area here of the tundra, and this is the area of Alaska that we're going to be looking at as we go through. Okay, so statement number one, temperatures are rising much faster in Alaska than in most other parts of the world. Let's take a look at some evidence here to help to explore that. What, in other words, are the actual impacts? What has already happened here? So if you come across climate change skeptics, you don't even need just to be looking at what's potentially going to happen in the future, although we will look at that. We can look and start off with what has actually happened. Is Alaska getting warmer? Well, let's take a look. And the analogy that I'm going to use as we go through this is that Alaska is kind of like a canary in a mine. This is a saying that comes from times, probably 19th century, whenever people would have gone down into the coal mines. And they didn't have the air monitors at that stage, so they would bring this little canary down with them, this little canary who you might think is just this lovely little pet there to help look after them and keep them company. The canary was there for one purpose and one purpose alone. If the air quality deteriorated in the mine, the canary would pop his clogs before the people would. If the canary stopped singing and they look over and see him lying on his back with his little legs stuck in the air, they know, uh-oh, air quality, we better evacuate. And we're going to discover here that because the rates of warming are so high in Alaska, Alaska acts almost like a canary in the mine for us when it comes to assessing what climate change impacts are going to likely be across the globe. If we let warming get out of hand, what kinds of things can we expect? This is the canary in the mine, the early warning of worse things to come. So, to practice your skills at resource analysis, we'll have a few resources, maps and graphs on the way through here as well to illustrate these points. Now remember, our main point here is temperatures are rising much faster in Alaska than in most other parts of the world. Does this map bear that out? Well, you can see the temperature anomalies, that temperatures are rising across the world, yes, but they are particularly rising here in the North Pole, in around about the northern Arctic areas. Temperatures are rising faster here than anywhere else in the world. You can see that on this map. You can also see something similar in this graph. It's going to take similar information that we've just seen in the map but presented a graph. Let's take a few moments to get ourselves orientated. This along the bottom is the equator, the latitudes, or I should say. So there's the equator, there's the South Pole, there's the North Pole. So this is heading from the equator to the South Pole. This is heading from the equator to the North Pole. What you've got here, latitudinal mean temperature rise. What's that all mean? Well, the mean is the average for each latitude by how much has the temperature risen from 1950 to 2017. So, if you go to 25 degrees south, temperature has risen by about 0.8 degrees. If you go to the equator, temperature has risen there also by about 0.8 degrees. So that line represents the increase. And you can see that from the South Pole up to around about 40 degrees north, there has been an increase over that time period, 2015 to 2017, of between 0.7 and 1 degrees, depending on your latitude, right? Oh, this area here is blanked out. I wonder, on the basis of this map, can you predict what this graph is going to do? Let's have a look. Whoa. Whoa. So at 55 degrees north, where Portrush is, that lovely little restaurant many will have been to, temperatures maybe about 1.6 degrees warmer. That's the temperature rise from 1915 to 27. But when you get up to above 75 degrees north and up towards the Arctic regions, you're getting close to 4 degrees warmer between the 1950 to 2017 average. Nearly 4 degrees. Look at that. Most of the rest of the Earth is less than 1 degree, but up here it's nearly 4 degrees. So our statement: temperatures are rising much faster in Alaska than most other parts of the world. I think we're seeing evidence for that, are we not? Let's take a look at the text. This is the text that you learn for your case study. The first actual impact of climate change is rising temperatures. Alaska has witnessed a notable increase in temperatures since the 1970s, with the statewide average temperatures now 1.9 degrees warmer than the early to mid 20th century. Twice the US average, but, and this is what was shown in the graph we've just looked at, winter temperatures have experienced an even more dramatic rise, increasing by nearly 4%. It's a crazy increase. This is a graph that graphs out the temperature changes in the long term. Now, again, this is a good bit of practice for you just your kind of digital literacy in a world where you're going to be bombarded by information. You can see here that this graph at first instance and first glance looks like it's going up and down a lot, which it is. There is a lot of variation in that. That's called the natural variation in the weather year on year. There's a whole bunch of reasons why any one particular year might be slightly warmer or colder than the other one. What are the trends in this graph though? This is the deviation of the average temperature from the long-term mean. So that's 1925 to 2020. That's the average temperature represented by 0 for that time period. If the line goes above it, it's above that average. If it goes below it, it's below that average. So what patterns do you see in this graph? Well, why don't we add in a trend line to help us to see this a little bit more? And you can see that up until around about the 1970s, the trend line here, this is a moving average trend line. The trend line shows that the temperatures dip up and below that long-term mean. Sometimes they're slightly warmer, sometimes slightly colder. That longer-term moving average. So just slightly above and below the long-term mean. Then there's a dip in temperatures in the 1970s, and then from the 1970s onwards, there's still that up and down, there's still that variation, but now if you look at it, most of that up and down is above the long-term average. Most of it goes up above. You can see here at this point it's up higher. Occasionally it will go down below, but most of the time the temperatures here are above the long-term average. So this isn't an easy graph to get your head around, but I'm hoping now you're beginning to see the change in the long-term average here, or the long-term trends, I should say here, from dipping up and down below and above the long-term mean to mostly above the long-term mean. The temperatures are rising. So, next point, spatial variations in the warming. The data show that winter temperatures in Alaska have warmed at a rate about 1 degree C higher than other tundra regions around the globe at the same latitude. This map is going to help us with this. It's similar to the map that I started the presentation with. Let's get your bearings. There is North America, there's Alaska, there's the British Isles, France, Spain, Scandinavia, and Russia round to Siberia, the North Pole, and this is the area that most of the tundra is found in. So what you can see here is, yes, still the northern polar Arctic regions are warming faster than anywhere else. We've seen that already, but especially this area here around Alaska, especially here. So it's not only is the North Arctic polar region warming faster, but within that, Alaska is warming even faster than everywhere else within that area. So that's what that sentence says. Data show that winter temperatures in Alaska have warmed at a rate about 1 degree higher than other tundra regions around the globe at the same latitude. There you can see it there. This warming has been more pronounced along the north slope of Alaska, where January temperatures have risen by 2.4. So not only is Alaska warming at a faster rate than anywhere else in the Arctic, the places where you've got tundra in Alaska are warming faster than anywhere else. There's 2.4, this north slope where you've got tundra, and down the western coast here where you have your tundra. So the Alaskan tundra is, tragically, I guess, the perfect canary in the mine. It's warming faster than anywhere else in the world, and therefore gives us a very good indication of what climate change is likely to have. So let's take a look at these potential consequences now. We've looked at the actual changes, the temporal patterns and the spatial patterns. Now what about the potential patterns? Projections for the future suggest that temperatures will continue to rise for the Alaskan tundra. For example, the average annual temperatures in Kenai, Alaska are projected to increase steadily to 2.3 degrees above their 2020s baseline by the 2090s. And that's what this graph is showing, this steady increase. And it is pretty steady, isn't it, compared to the other graphs we're looking at? It's a pretty steady increase going up over time. So the actual temperatures have already risen faster than anywhere else in the world, and the future projections are for that to continue to increase, and that's going to lead us to this cascade of catastrophic consequences. Please learn that phrase and include that phrase in your essay. I think it's a powerful, evaluative phrase. The temperatures are rising, therefore there's a cascade of catastrophic consequences. Here we have it. That's powerful little phrase. Okay, let's move on then to the second one. First statement was temperatures are rising faster in Alaska than most other parts of the world. The first of those consequences is that tundra is seeing significant wildfires in a way not experienced in the past 11,000 years. That's our second evaluative statement. Learn that and make sure you can repeat that in the exam. So the first of these knock-on effects is an increase in wildfires in a scale not seen in the Alaskan tundra since the end of the last glacial period, since the end of the last ice age. That's why I picked the 11,000 years figure. These can be triggered when you get a natural ignition source, so lightning, whenever it strikes a fuel source, which is duff. Now, I hope you remember from when we looked at the soils in the tundra, the duff is the semi-decomposed organic matter that's just sitting on the top of the soil. If you get more lightning, and if the duff dries out, you're going to have more wildfires. And guess what? Spoilers, that's kind of what's been happening. Both of these are impacted by climate change. Here's the number of wildfires in Alaska over time. And we add in our moving average here, and you can see that the trend is for that to have gone up from the 1970s, which was exactly the time whenever the temperature started to kind of have that noticeable jump up as well. So there's definitely a correlation here between the number of wildfires and that increase in the temperatures that has caused them to spike. Again, there's variation. Look at that, year on year. Of course there is. It's this natural system. There will be variation, but look at the trend. The trend, nevertheless, is pretty clear. When you smooth that out even further to a polynomial trend line, the trend becomes even more apparent of that increase over time. So the increased warmth and summer convectional storms causes an increase in lightning strikes, covering a larger geographical area, including places that would not have typically had them before. So here's the number of lightning strikes from 1986 to 2010. That's the best data set I could get. 87 and 89 are no data, by the way, not no lightning strikes. But there's the trend line there. You can see that the number of lightning strikes is definitely going up. Here's one particular example of a recent one. For instance, between the 2nd and 4th of July 2022, over 17,000 lightning strikes were recorded in Alaska in those 3 days, including a concentration in areas that don't normally get them. For example, the northwest of the North Slope, which is one of the tundra areas. There's the lightning strikes in those 3 days, and there is that concentration in the tundra area. You're getting more lightning strikes, and they are occurring in areas that are not typically affected by lightning strikes to the same extent, including the tundra areas. Here's some satellite imagery of the fire burning on June the 10th, 2022. You can see this very clearly from space. So you're getting an increase in lightning strikes covering areas that are not normally affected. But what about the duff? Secondly, the warmer conditions dry out the duff. There it is. This duff that dries it out more and gives it this fuel to burn. So you have this bizarre thing that whenever a wildfire starts, you can see them there. They start and they may appear to go out. These aren't huge, big, raging firestorms that you might expect to see, because this is burning kind of very low-level vegetation. It looks, let's go back to this image here. Yeah, it looks more like that. And it can appear that those fires go out. It appears that they would end. But what actually is happening is that below the surface, the duff can smoulder for days and for weeks, which can result in zombie fires. I'm recording this just after Halloween, so it's quite appropriate. Zombie fires, where the fires that appear to go out reignite later as the duff below the surface was still smouldering. So you can get an increase in the lightning strikes. You can get them occurring in places where they haven't occurred before, and the duff will dry out. The lightning strikes the duff burns more easily and burns for longer, including those zombie fires. Now remember, we're looking here, folks, at things that have already actually happened. We're not looking at things that are into the future as yet. So let's evaluate those actual impacts. We're already seeing the actual impacts of wildfires. Wildfire in the Alaskan tundra has been a rare occurrence in the past 11,000 years, but let's take a look at one of the biggest ones in recent decades. 2007, the largest ever tundra fire in the North Slope region of Alaska, the Anatuvuk fire, caused by a lightning strike, burned an area over 1,000 square kilometers. To give a sense of scale, that's more than doubling the area that's burned in the region since the 1950s. One fire was equivalent to twice the total amount of area burned in the previous 50 years. It's a massive, massive scale. And there you can see it. That's that one fire up there. Most of the wildfires, as you can see, are not in the tundra areas in Alaska, than the forest fires, but you're getting an increasing number in the tundra, which is this light blue area, including this Anatuvuk fire. Zoom in a little bit closer, you can get a bit of a sense of the scale of it. There's the scale down there. So the length of that, what's that look? 50 kilometers long? This is it from satellite image in space. Again, you can just see the burn scar that has been produced by that. And here's some more satellite images of it actually in its burning phases. Okay, so fire. What are the impacts of this fire? It had devastating impact on carbon storage. This was one academic study in 2011 by Mack et al. Revealed that the fire released 2.1 million tons of carbon into the atmosphere. Now that does sound like a big number because I've got the word million in there. But let me give you a real sense of just how big it is. This was as much carbon as that the entire Arctic tundra had absorbed in the previous 25 years. Now pause and let that sink in for a moment. The Arctic tundra, like any natural ecosystem, takes in carbon as a part of the process of photosynthesis and becomes a carbon store. In that one fire, the carbon that was released was the equivalent to what was absorbed into the carbon store in the past quarter of a century, not just for Alaska, but for the entire Arctic tundra. And with figures like that, we begin to see why it is that the Arctic is warming as quickly as it is, because that incredible amount of carbon released into the atmosphere has really significant impacts. So those are the actual impacts: increased lightning, wider geographical areas, zombie fires. Here's the Anaktuvuk fire as an example of that in 2007. What's it look like looking ahead? What is the potential for the future given these trends? Evaluating the potential impacts. So this Anaktuvuk fire gave us an important opportunity to evaluate the potential impacts. So this study by Mack of 2011 tried to do just that. The carbon emissions, they found the carbon emissions resulting from wildfire burning were 30 to 50 times higher than the rate of carbon emissions from a natural ecosystem decomposition. So as part of the nutrient cycle, whenever the vegetation decomposes, the carbon that was absorbed, some of it is given back off again. That's part of the carbon cycle, it's part of that nutrient cycle. So there is a natural emission of carbon, an output of carbon as well as storage of carbon in these natural ecosystems. But when you burn those, when that fire occurred, the output was 30 to 50 times higher than the natural rate, which means that if you get more fires, you get a lot more carbon emitted, which is going to increase the temperatures in the area significantly. Additionally, they explored the potential impact of burning on climate change feedback loops. Right, let me just pause for a second here and explain to you what a feedback loop is. If you've ever been in an event where somebody is at a sound desk and they turn on the microphone and the person at the front is speaking and you start to get this high-pitched whining noise that gets louder and louder and louder, and it's very, very unpleasant, this squealing noise, that's feedback. It's used intentionally by electric guitar players at times as well to get that lovely, pleasant sound when an electric guitar player can control it well. But that horrible squealing sound in an event is anything but pleasant. And the way the feedback loop goes is like this. The microphone basically is turned up. It's too sensitive. So the person speaks into the microphone. That signal is taken into the speakers. It's amplified out into the hall. And that amplified sound comes back into the microphone, which increases the volume going into the microphone, which increases the volume coming out of the speakers, which comes back into the microphone, which increases the volume going into the microphone, increases the volume coming out of the speakers. You get the sense there. This feeding back in, what comes out, comes back in again, and amplifies the change. What comes out, comes back in again, and amplifies the change. So whenever it comes to climate change, you can get these feedback loops happening. You'll introduce a change into the ecosystem, and that change will act to reinforce the change, making it amplified and worse. Now, a positive feedback loop produces a reinforcement of the change. It's not positive because of its outcome, it's positive because it positively reinforces and promotes the change. The positive feedback loop makes the change bigger. A negative feedback loop is not negative because of its outcomes, it's negative because it tends to counteract the change. So you actually want negative feedback loops because they counteract the change, and you want to avoid positive feedback loops because they amplify the change. Okay, good news is that you're not ever going to have to explain that in the exam. You can just write about feedback loops and the examiner will know about them, but I just want you to understand a little bit about what they mean. They are really, really important, I think, in you understanding climate change, because what you can have are these unintended consequences, these positive feedback loops that reinforce the change. Right. That said, let's have a look here again at our sentence. Additionally, Mark et al. Explored the potential impact of burning on climate change feedback loops. While there's a potential negative feedback loop, remember that's the good one, exists in which the grassy tundra may be replaced by shrub tundra acting as a biomass store of carbon. Okay, so grass is replaced by shrubs. Shrubs are bigger, so the biomass store increases. Yay, that's good. More carbon stored. Not quite. They found that the dominant feedback loops appear to be positive. Remember, those are the ones we don't want because they reinforce the change. The increased carbon store in shrubs would be offset by a reduction in the soil carbon storage. Let's have a look at that. Here we go. This is the burning that takes place. Then after the burning, the shrubs grow, the biomass store increases, absorbs more carbon. Yay! Oh dear. But the soil store decreases, cancelling that out. So it looks like before the burning, here comes the burning, afterwards the shrubs, looks like we're getting that lovely little negative feedback loop, but no, actually what happens is that the soil store decreases. Watch it, here we go, down here, soil store is going to decrease. Cancelling that out. So the increased carbon store in shrubs would be offset by a reduction in the soil carbon storage. That's the feedback loop, a positive one that reinforces the change. Then the second one is that the darker shrubs' lower albedo would absorb more of the sun's heat, leading to regional warming of the tundra. Let's explore that. So before the burning, with the grasses, they're lighter, so they reflect more of the sunlight and absorb less heat. They're replaced by shrubs which are darker. Dark colours absorb more heat, so there's less reflected and more heat is absorbed locally in the area. So there's before the burning, the grasses, lighter colour, the more heat reflected, less heat stored locally. They're replaced by shrubs which are darker. There is less of the heat reflected, more heat is absorbed locally. So back to this statement. The darker shrubs, lower albedo. The albedo is how much is reflected by its surface. The darker shrubs absorb more of the sun's heat, leading to regional warming. Now, just in case you're looking at that thinking that there's a lot to take in there, most of what I've said in the last 4 or 5 minutes have been explanation, so that whenever you're reading this you understand it. In the exam it's absolutely fine for you just simply to have learned that and to have repeated that. There are climate change feedback loops which are mostly positive. Those are the ones we want to avoid. The increase in shrub storage is offset in reduction in soil storage, and the darker shrubs absorb more heat, lead to regional warming. That's the point that you would make. Okay, so that's that second point. The first of our cascade of catastrophic consequences. The tundra is now seeing significant wildfires in a way not experienced in the last 11,000 years. There's been an increase in lightning over a wider geographical area, which has produced also these zombie fires. There's the Anaktuvuk fire in 2007 as the actual example, and then in the positive feedback loops, the soil store decreasing and the albedo from the shrubs, meaning that more heat is absorbed, which is going to lead to more localized warming. Right, that brings us then to the last point that we're making. Temperatures are rising faster in Alaska than most other parts of the world. That leads to cascade of catastrophic consequences. One has been wildfires. Now we're looking at permafrost thawing. Don't say melting, say thawing please, at an alarming rate, setting up some more concerning positive feedback loops in motion. So again, what's the actual, what's the potential? So Here we go. The second knock-on effect is permafrost thawing, and we are already seeing impacts. The concentration of heating along the North Slope, remember, we saw that within Alaska, the North Slope is warming more than anywhere else, means that thawing is being recorded at depths down to 10 meters. In that annual climate variation between the summer and the winter, the summer comes along and there tends to be a little bit of thawing of the permafrost, but with the warmer temperatures, that thawing is occurring to a much deeper level, down to 10 meters. This is well below where seasonal thawing would typically occur. Here's a particular example. Dalton Highway were warned by from 1 to 3 degrees between the 1980s to 2018. Further projections suggest that soil temperatures will continue to rise, especially along the North Slope, resulting in further permafrost thawing. Here's projections for the 2090s, suggesting that temperatures at 2 meters deep along most of the North Slope would be above freezing. That's crucial. If they're above freezing, then they will no longer be permafrost. Here's a GIF showing that, so you can just see the differences in the temperatures over time. This is the 2090s. This is the North Slope tundra area. Here's the 2000s, and this is the temperature at 2 meters. And anything red is above freezing. The yellow is just sitting around about freezing as well. So you're seeing at 2 meters depth, there are very, very few places left in this North Slope that'll have at 2 meters depth any kind of permafrost. That's a hugely significant change in the ecosystem. So let's take a look at the thermokarst lakes and thaw slumps. Here's the actual impacts. The melting of the permafrost in Alaska has had predominantly actual negative consequences for the local tundra ecosystem. The interdependence of plants like sedges and dwarf shrubs and animals such as lemmings and Arctic fox relies on a delicate balance in the tundra ecosystem. However, the ongoing melting or thawing has led to a noticeable rise in the number of thermokarst lakes. These lakes are altering the ecology, creating a more aquatic environment in certain areas, which in turn degrades the habitat for the tundra flora and fauna. This is the formation of the thermokarst lakes. You'll not need to explain this in the exam, but just shows you how it happens, where you've got these ice wedges here which begin to melt and they grow in size and you get these large lakes forming. Here's a before and after, 2010 2012. You could, if you fancy, pause the video and do a spot the difference. You can see the areas where the lakes have grown in size even in those 2-year periods of those thermokarst lakes. Moreover, landslides known as thaw slumps have become increasingly common due to the unstable ground, exposing bare soil and disrupting the natural order. Studies indicate that secondary succession resulting from these changes reflects these aquatic conditions, which leads to shifts in the dominant plant species. So you can get a bit of a sense of the scale of these. These are huge, some of these, really, really large, where you can just see here where the soil is just slumped down because of the thawing of the permafrost. It becomes more unstable and down it goes. Look at the scale of this. Look at the size of that slump that has occurred there. These are massive, massive big features. Again, you can see some people in there, giving a bit of a sense of the size of it. So you're getting thermokarst lakes and you're getting thaw slumps. Those are already happening. In the future, this is likely to set up some more of these positive feedback loops that reinforce the change. Those, remember, the ones that we don't want. Both landslides and thermokarst lakes pose even more concerning potential future impacts. Scientists are concerned about the potential initiation of positive feedback loops. So the thaw slumps, these landslides, and remember, if we were to put a little person in there, you get a sense of the scale of these. They expose previously frozen ground, which is rich in organic matter. These are now at the surface, accelerating decay rates, which of course emits carbon, and which is going to feed into the carbon dioxide, which is going to feed into the localized warming. That is going to amplify the changes. A positive feedback loop that you want to avoid. Simultaneously, the meltwater and thermokarst lakes will speed up the permafrost thawing. The meltwater will thaw out the permafrost. If it thaws out, then the carbon stored in the permafrost is given off into the local area, amplifying the warming. This is the positive feedback loop that reinforces the change that you want to avoid. These two processes contribute to the release of more carbon dioxide and indeed methane. We haven't even really talked about methane. It's a massive area in itself. While the precise amount of carbon dioxide likely to be released due to melting is uncertain, we do know that a substantial amount of carbon is stored in permafrost at an estimated 1,500 gigatons. Now again, that number sounds big, but let me give you something to grasp how big that is. This is twice as much as the entire atmosphere currently contains. That's how much is stored in the permafrost alone, in the tundra. The potential for amplifying global warming trends, not just regionally in Alaska, but globally, is severe. If this melts at a large scale, at a fast rate, it is going to put in an incredible amount of carbon into our atmosphere, which is going to lead to this cascade of catastrophic consequences, this feedback loop. Sometimes people talk even about this concept called tipping points, the feedback loop that, or the change that is introduced becomes irreversible, it becomes inevitable, you can't stop it. I've not read anything yet that suggests that we've reached any of those tipping points, but this is the canary in the mine for us. It's warning us of what we need to be aware of whenever you see figures like that. So, our conclusion: Alaska tundra is the canary in the mine. It's warming faster than anywhere else, and it should be this opportunity for us to reflect. Should we be doing more about climate change than we are? Should we be taking this threat seriously? Well, the answer is obvious, isn't it? In conclusion, the climate change is having a substantial actual impacts already in the Alaskan tundra, with rising temperatures leading to increased wildfires and permafrost melting. The potential consequences are equally alarming, with feedback loops exacerbating the effects of climate change both regionally and globally. Okay, let me finish by summarising this. There's a lot of detail in this case study, folks, and I think it's one of those things that's important for you to be aware of, right? I think this is just important in any education. So I'm happy that I get a chance to talk about these things with you, difficult as they are to hear, because I think we need to know them. But I am aware also of the fact that you've got an exam coming up on this, so how do we write this in the exam? And this is why I've been going over this all the way through, for you to keep your focus clear on this. The temperatures are rising faster in Alaska than most other parts of the world. We have seen this, the actual temperature rises, the spatial variations, that Alaska is warming faster than anywhere else in the North Pole and in the northern Arctic areas, and the tundra areas within Alaska are warming faster than Alaska on average. The potential is looking like, yes, those temperature rises will continue. Their evaluation is this cascade of catastrophic consequences. So the tundra, the first one, the tundra is seeing significant wildfires not experienced in the past 11,000 years. So increased amount of lightning covering a wider geographical area, including these Duff-related zombie fires. Our actual example of this was the Anaktuvuk fire in 2007. The potential in the future is these positive feedback loops, the one we want to avoid. The soil store decreasing, giving off more carbon, the albedo being affected, the shrubs absorbing more heat, leading to localized warming, reinforcing the change. And the second catastrophic consequence is the permafrost thawing, not melting, thawing at an alarming rate with some positive feedback loops. So we looked at the thermokarst lakes and the thaw slumps, and the fact that they will be are increasing, and the potential in the future is that they lead to your positive feedback loops, that the thermokarst lakes and the thaw slumps are basically releasing a lot more of the carbon that's stored in the tundra biome in Alaska, leading to not only localized warming but potentially global warming as well. So that is our case study. The video here is to help you to really grasp and understand this important issue. Whenever it comes to preparing for the exam, go and take a look at the notes that you've got on it. Go through those. If you understand what I've covered in this video, those notes should make sense for you. Those are the notes to learn and to keep on top of, so that you're well prepared for tackling any questions you get in the exam on this. So that is, I think, yeah, everything that I need to say on the case study.